Good morning, good afternoon, and also good evening. We are here in the talk number 5 today. Thank you for you to be here with us. And now we have two messages from two of our main sponsors.
Good morning, my name is Paolo Gamba and I am the president for the year 2020 of the Geoscience Remote Sensing Society. Okay, so first of all, what is a scientific society? What is GRSS? So a scientific society is a group of scientists, researchers and practitioners with common interest and common framework for building a community. In our specific case, we are people who are dealing with theory, concept and techniques of science and engineering as they apply to remote sensing of the Earth, ocean, atmosphere and space, as well as the processing, interpretation and dissemination of this information. So what are the activities of the IEEE Geoscience and Remote Sensing Society? Well, we have a number of applications. We support conferences. We have professional activities. We have a number of information service and technical activities and education activities as well. We are a global community, which means that we are arranged around a large number of groups of people that we call chapters all around the world. We have currently more than 90 chapters all around the world. As a result, GRSS disseminates premium science by means of its three main journals, which are the Transactional Geoscience Remote Sensing, the Geoscience Remote Sensing Letters, the IEEE Journal of Selected Topics in Applied Earth Observation and Remote Sensing, but we have also a magazine, which, by the way, has a very, very important role. We also provide opportunities for the different communities, like, for instance, the community working on image analysis and data fusion. We also sponsor community-driven events, like the very successful Earth Vision workshop, but also the SpaceNet Challenge data challenges here, which is organized by SpaceNet. We support also community-developed tools like the DESE website, which is Data and Algorithm Standard Evaluation website, and also activities related to RFI observations. So we also facilitate and connect. We have a number of activities at in our main conference. We have the so-called TIE events, but we also organize different events related to connection with companies, industries. We have a number of activities like for young professionals, for women in engineering and in geoscience and remote sensing. And we share our knowledge on hot topics by means of distinguished lecturers and industry speakers. We have also a number of educational activities. This is one of them. This is basically, let's say, one of the many different small educational videos for kids that we have in different languages, but we have also, in addition to that, a number of webinars, which are also for people who are not kids, about remote sensing in different languages as well. We offer continuing education by means of webinars, which is especially important and useful in this situation where we are not able anymore to move around the world as we were in the past. So we can support continuing education of students and young professionals through conferences, journals, our magazine, webinars, and so on. We can promote capabilities of the different communities, algorithms, data set by means of the data fusion context, by means of dedicated events at our conferences, by means of the industrial distinguished lecture or industrial speakers. We help connect companies and young motivated people by means of the young professional event, by means of student grants, by means of the TIE forum. And we make the different community of Earth observation practitioner and researcher be aware of their and your topics of interest. So GRSS is actually a community of communities where we could together share and promote ideas, systems, and data set, We can meet with other communities and gain from their perspective, and we can build different collaboration to learn more from each other's and to come together in conferences. Thank you very much, and I hope you will enjoy this summer school and all the interesting topic and talks that you are going to listen during these days.
Hi everyone, my name is Cheryl Rose Reyes, and I currently serve as the president of the International Society for Photogrammetry and Remote Sensing Student Consortium. I am very happy to welcome you all to the 6th edition of the IEEE-GRSS Young Professionals and ISPRS Student Consortium Summer School this year. To start this event, I would like to present a bit about the ISPRS Student Consortium. We are the official representation of the youth to ISPRS. We link students, young researchers, and professionals worldwide interested in photogrammetry, remote sensing, and spatial information science to promote their scientific and professional developments. We advocate imaging and geospatial science for informed, scientifically valid, and technologically sound observations of Earth conditions and trends that lead to improved and effective decision making. The consortium is also accepting registrations for individual membership. Please scan the QR code in this slide if you are interested to join us. I work together with members of the board of directors from all across the globe. Charles from Uganda is our vice president. Charmaine, who is currently in Ireland, is in charge of our newsletter. Mustafa, our social media administrator, is from Turkey. And finally, Sona from Azerbaijan is our web administrator. One of the major events that we host and coordinate every year are the summer schools. In 2019, the summer schools were in Uganda, Poland, South Korea, and Brazil. These summer schools provide international learning opportunities for students and young professionals at a minimum cost. This year, we scheduled 3 summer schools, but due to the COVID-19 situation, 2 of them were postponed, and we are sincerely thankful to the organizers of this summer school for making this an incredible virtual event. This is the first ISPRS Student Consortium Summer School that will be hosted online, and as you can see, we have an amazing lineup of speakers who will deliver lectures on remote sensing and machine learning. The consortium currently hosts the virtual rooms and the webinar series to provide our community with more opportunities to learn and interact with experts in our scientific community. The webinar series was conceptualized in 2018, and we have organized webinars on Google Earth Engine, computer vision, and machine learning. The virtual rooms is an initiative to keep the members of the consortium connected during this challenging time and to help them navigate our changing lifestyles. All the resources for the webinar series and the virtual rooms are available on our website and our YouTube channel. We also publish an official newsletter called Spectrum, which covers the broad applications of remote sensing, photogrammetry, and spatial information science, and welcomes contributors from diverse backgrounds and disciplines. We publish 4 issues a year, and our most recent issue is related to the current pandemic and the significance of geospatial information in tackling the impacts of this global health crisis to our society. The ISPRS Congress is one of the biggest gatherings in our scientific community, which is held every 4 years. The Congress hosted a virtual event for all papers submitted this year and postponed the in-person meeting for 2021. During the Congress, the consortium will be hosting a 3-day youth forum, which will feature the following activities: speed dating, technical sessions, a special session on women in remote sensing, photogrammetry, and spatial information science, a panel discussion, the General Assembly for our members, a student night, another summer school, and will co-organize a mapping party. The consortium would also like to invite you to nominate papers for the Excellence Award to be given during this event. Please scan the QR code for eligibility and nominations. Also, please visit the ISPRS Congress official website for updates. Finally, I would like to invite you all to join our communities on Facebook, Twitter, and to visit our website for all the information shared in this presentation. And again, I would like to invite you all to register as an individual member by scanning the QR code on the right. This is the end of my presentation, and I wish you all a meaningful summer school. Thank you very much.
Thank you, Cheryl and Paolo, for your messages. Now, I would like to introduce you Professor Mauricio Gallo and also the PhD student, Nayara Strabs. Professor Mauricio is from São Paulo State University. He's an expert in photogrammetry. Nayara is the president of the IEEE Geoscience and Remote Sensing Society student chapter here at Federal University of Mato Grosso do Sul. They're going to chair this section with me. Thank you, Mauricio, and also Nayara for being here with us. And now I would like to introduce our speaker, Anette Eltner. Anette is from TU Dresden, where she is a postdoc. She got her PhD degree in 2016 at the same university. In 2017, she got a very interesting prize of German Geomorphology Association for the best PhD thesis. Anette is a well-known researcher. She was here in Brazil in 2018 at Federal University of Mato Grosso do Sul. And it's a great pleasure to receive you here, Anette, and thank you again for accepting our invitation. It's your time. Thank you.
Thank you very much for your very nice introduction. And thank you very much that I can be part of this here today. And now I want to talk about UAV remote sensing for hydro-morphological monitoring. And thereby I want to introduce a few methods, but also very strongly I will focus on the applications. And more specifically, what I'm going to talk about is how to use UAV data on the one hand to measure topography and the bathymetry of river reaches, and also how to use UAV data to measure flow velocities and discharges. And for the flow velocity and discharge measurement, I will further talk about either using RGB imagery as well as thermal imagery. Now, UAVs have been noticed in the field of river monitoring quite early due to the capabilities of UAVs to close the gap between satellite measurements at larger scales and the terrestrial mapping at the very small scale. And due to the flexibilities of the UAVs, they can be applied very frequently and therefore allow for a very good monitoring, which is amongst others very important to analyze the ecological conditions of river habitats. And now different parameters can be observed with the UAV. For instance, of course, topographic surveys can be performed. And if you do it multitemporally, then of course you can also do geomorphic change detection. Another thing which UAVs are very suitable for is to use them for grain size mapping due to the very high resolution of the UAV images. And another example is the usage of bathymetric LiDAR systems to measure the points under the water and to reconstruct the riverbed. And also, of course, you can use the UAVs to, due to the frequent mapping opportunity, to monitor the restoration, how well restorations are progressing. And within this talk, I want to focus on 3 case studies to illustrate how well you can use the UAV to perform the mapping. And on the one hand, there's going to be a small river reach of a length of about 300 meters, which has been monitored in Germany at the Freiberger Mulde. And a second river, which has been monitored in Hungary, it's the Sajo River. And this is a meandering river. And the river reach has a length of about 600 meters. And the third river, which were monitored with UAV data, is the Pulmanki River in northern Finland. And here the river reach, which has been observed, has a length of about 1 kilometer. And now these three different sites are chosen also to show the different limits of the methods. And of course, the first thing that has been done at each river was a standard orthomorphic mapping of the area of interest, which means that, of course, you perform a flight plan at the beginning. And then, as you can see here, these are the white dots are the image positions or from the locations from which images were captured. And then at the three different rivers, they were captured from flying heights between 50 to 100 meter, resulting in ground sampling distances of 2 to 3 centimeters. And the overlap between the images was 85% in flight direction and 70% of the stripes. And of course, you also have to consider very carefully the GCB, ground control point distribution, especially if you follow an elongated river section. And so here, as you can see, just an example, the red dots are ground control points, which were at the corners of the area of interest and also along the sides of the area of interest. And here's now the result for all three rivers for the topographic mapping at each of the site. And you can see now that it's quite well suitable using just the standard UAV photogrammetric workflow, which I'm not going to go into detail here, but maybe if you have questions afterwards. And also you can see now here in these three figures that also the area where the river is flowing, so the underwater areas have been also reconstructed with the structure for motion or UAV photogrammetry approaches. But it has to be noted here that these points underwater are yet faulty. And why is that? Because the typical structure for motion or photogrammetric tools which are used to do these reconstructions from the UAV images do not consider the impact of the refraction, which describes the circumstance that the light ray changes the direction when the medium changes through which it travels. So here in this case, as you can see, if you do not consider it, as shown here in blue, you would underestimate the water depth versus the situation when you indeed consider the refraction of the ray of light and then having the correct water depth. And this circumstance, of course, has been known already for quite some time in the discipline of multimedia photogrammetry, which acknowledged that the basic assumption of the collinearity constraint that the image point, the camera projection center, and the object point are on a straight line is not fulfilled anymore. And now, of course, you can, however, describe this circumstance with the so-called Snell's law, and which describes the relationship between the angle of incidence and the refraction of the light ray passing through a boundary between two different media. So it basically connects the different incidence angles. And now if you do know this circumstance, it's also possible to correct now the underwater points. Further, what has to be said, the incidence, the stronger the incidence angle is at the water surface, the stronger will be the deflection of the ray of light. And also you have to consider for the correction the different refraction indices of the different media. Here you see the refraction indice of air is 1, whereas of fresh water is about 0.33. But it has to be considered for the freshwater. For instance, if the salinity changes or the temperature, also these refraction indices are going to change. Now, because it's possible to model these refraction, it can also be implemented in the photogrammetric workflow. And one simple approach would be just to assign a correction value to the wrong heights of the underwater points, based on the knowledge about the known camera pose as well as water surface location. Of course, there are also more sophisticated approaches which actually implement the refraction aspect into the bundle block adjustment, which then also allows for the estimation of the location of the water surface as well as of the incidence angles. But this is going to be out of scope of my talk here today. However, to do this modeling, one assumption has to be met, and that is that the water surface is a planar surface. So you can only do this for very calm water surfaces. And furthermore, to apply this approach, you also have to see the riverbed very well, of course, to perform the point matching, and so have to see a good texture in your images. And therefore, the turbidity of the water cannot be too high, and it's also only limited to a specific water depth. And here's now what, as mentioned, you need to know the water surface. So here's now an approach shown what would be a possibility to get the water surface. So one approach, but of course a simple one, would be just manually clicking the 3D points in your point cloud, which form the border between the water and the surrounding land. But this can become very time consuming with the longer river reaches and if the complexity of the river reach is increasing. And there are also automatic approaches which you can use, which is here now illustrated for a very simple approach by just considering the color ratio between the red and blue. And as you can see here now, the blue signature is showing you it's very well distinguishable, the water area from the land area. And then you can extract the 3D contour, which is shown here if you use this color ratio. And at the end, you just mesh the points, and then you have your 3D, then you have your water surface. However, you don't have always the condition that it's such an easy approach just to combine two colors to get the water surface. And there are many more complex scenarios where that is not applicable. And in these situations, it's suitable to apply one of the more recent approaches by just using convolutional neural networks to automatically segment the water area. And this is now here illustrated for a terrestrial camera. So here you can see this is a Raspberry Pi camera, which has been capturing the river area. And then a CNN has been trained with the time series of the images capturing the water. And then on the right side here, you can already see the result of the trained CNN then applied to unseen images. And you can also very well see that this approach is very robust. So it does not matter if you have shadow or sun of the river, it's still able to segment the water area. And here the comparison between ground truth data and the classified water data, the accordance was between 97 and 99%. So it is a very very accurate. And in the next step would be now to actually apply these CNNs also to UAV images to automatically segment the water area. And furthermore, as already mentioned, the visibility of the riverbed is also important. And there are also processing workflows you can apply to improve the visibility of the riverbed. As you can see here now in this example, you have quite a lot of waves due to ripples, and which cause shadow or foam on the surface, which hinders a good visibility of the riverbed. And now here the idea is just to use the UAV to fly along the river reach again, and this time capturing a video. And then you extract the frames of the videos and you assign the first frame as a head frame and co-register all frames afterwards to this first frame to mitigate the impact of the UAV movements. And you do this co-registration in such a way that you detect features at the shore sites. And but however, as you can see here, there are also some features in green which were detected in the water area. But during the next step, which is the matching step, where you're using multidimensional descriptors of these features and you're matching them, these points in the water are going to be eliminated because the water is moving and therefore changing its appearance from frame to frame. And those points are then automatically already identified as outliers. So you only use these points in the shore area to then perform the matching. And if you have found the corresponding points, you then can perform either a affine transformation or a perspective transformation of the subsequent frames, though they fit to the head frame. However, this approach assumes that all the points are laying within a plane. So if you go to rivers where you have a very strong relief, you will reach the limits with this approach here. And now here you can see the frames have been co-registered, and in the next final step you calculate a median image, which means you stack all the frames together and then calculate for each pixel the median, which results whose result you can see down here, that all the wave shadows are nearly removed and also particles on the surface have been removed. And if, for instance, you look at this area over here, you can see that the visibility of the riverbed has been also improved. And now here you can see the results with at which now the underwater points have been corrected and also these median images have been implemented. And you can see very well that the water depth could be reconstructed at all 3 sites. But you also see at the river here in the middle, at the river in Hungary, that you do have some gaps as well in the riverbed. And which is here due to the circumstance that the depth, that the turbidity of the water here at the Sayo River was higher compared to the other 2 rivers, and therefore already at a lower water depth, you were not able to reconstruct anything anymore. Well, of course, now we have the water depth reconstructed, but we also have to see how accurately this approach is actually performing. So in the next step, here in these 2 study sites in Hungary and in Finland, there were reference data captured. On the one hand, RTK GNS points were measured, which are here illustrated in blue, at the Puolmanki River in Finland, which you can see down here is their distribution. And as well, ATCP measurements were performed, and ATCP is an acoustic Doppler current profiler, which uses basically sound waves to measure the water depth. So the travel time of the sound waves when they're going forward and getting back scattered from the ground. And these are the white points here in both figures illustrated here, 2 cross-section and some more areas at the Puolmanki site. And now here you can see the comparison between the RTK GNSS points at the Puolmanki site. And you can see here in gray, these values are the uncorrected water points under the water, and in blue are the corrected points. So you can already see the shift accordingly here. And if you also look now here into the table, you can see that the deviation between the RTK points as well as the UAV points are decreasing significantly between 17 and 16 centimeters to 5 and 3 centimeters. And furthermore, what you also can see is that the implementation of these median images are also increasing the performance or the accuracy of this approach, as you can see here in raw, which means that the frame has not been processed, and in median it will be the filtered image. So improving the visibility of the riverbed results also in some more points and more precise points. And now here's the comparison to the ATCP. And as for the RTK points, you can see that the accuracy has been improved significantly. And for the Puolmanki site, up to now 5 centimeter average deviation, and at the Sayo site, about 10 centimeters. So you can see that at the Sayo site, the error is still a little bit higher compared to the Puolmanki site, which is amongst others, due to the turbidity, which I already mentioned, which also caused larger data gaps in that data set. So the turbidity is a very important aspect to consider with this workflow. And besides now using average values to assess the accuracy, now it's also useful to see if it's possible to assess the spatial distribution of the error between the UAV data and an independent reference. And here, this reference is a boat measurement. So this boat has been equipped with an echo sounder, which with a single beam sonar, which is used along, again, the river. It was used along the river in a zigzag manner to collect the underwater points. And if you look at both the results from the boat as well as the UAV, you can see, of course, that the spatial pattern do match. But you can also see, especially down here, that there are still some errors within the UAV data, and especially here are some outliers, which are due to some shadows which were casted by trees onto the river. So there's also some more work which has to be done in this regard. And now I want to come to my second point, which is the aspect on how to use UAVs also to measure flow velocities. So this is especially important for many hydrological tasks, amongst others to retrieve the discharge of rivers, but also getting spatially distributed flow velocity fields are important for hydrodynamic modelings of rivers. So this is an valuable information in this field of application. And now I'm going to talk about how you can use either RGB or thermal images to get flow velocities from UAVs or apply to UAV data. And I'm going to talk about, on the one hand, how you can use particle tracking velocimetry, which basically means that you're tracing single particles on the water surface, and particle image velocimetry, where you are tracing patterns on the river. And it's I will introduce the workflow to a UAV data which has been captured by an UAV hovering at a stable position. And then later we are going to transfer this approach for the entire river reach. And the PTV workflow I will illustrate for RGB imagery at the Freiberger Mulde, the river in Germany. And the PIV workflow will be applied to thermal imagery at the river in Hungary. And now the first aspect, again, also the UAV has been tried to let it stay stable above the river. You can still see here that there are movements which have to be mitigated in a first step. And therefore, again, co-registration is applied in the same way as it has been used to calculate the median images. And now this is the result of the co-registration. And you can see that the shore is nearly stable, and you can now focus on the analysis of the water area. In the next step, it is important to mask the shore areas, because afterwards there will be the step that you are detecting features within the image, but you only want to find features in the water area, and you have to remove the area outside the water, which usually have a lot higher texture, and therefore usually a lot more points would be found in these areas outside the water. So to focus on the water area, you are masking it first, and then you extract features in the water. And either you can use your standard feature extractor like the Harris corner feature detector, or another approach, feature detector, which is basically the circumstance that you're looking for strong gray value gradients in at least two directions. So to identify single features or single points on the here on the water surface. And of course, you also for the rivers, you can as well use another workflow, because usually in the rivers you have the circumstance that you have very light particles on a dark background. So another very simple approach would be also just to binarize the radiometric information by applying a threshold. And here, as you can see, to separate particles on the water from the background. So this is in many applications also very suitable for flow monitoring on rivers. And after these features have been now detected, they have to be matched to or they have to be traced through the next frame, and then through the next and through the next. So you have to search now for this one feature extracted in the first frame. You have to find the location where it is in the second frame. And one approach would be an area-based approach, which implies the general idea to find location of the highest similarity by sliding a little picture. And this would be here now extracted a feature and its surrounding extracted in this image, as you can see it now here enhanced, and now sliding it through the next frame and searching for the highest similarity. And this comparison is done by convolution to, at the end, retrieve a similarity value at each pixel. And here you can see a 3D representation of this new image, which has been calculated with the correlation values. And the peak in this area is going to be the position in the new frame where the particle has been tracked. And here, this is now illustrated for the normalized cross correlation. which means it also considers that you might have different brightness or illumination differences between different frames. But of course, there are also many other matching approaches which you can apply. And as a result, you can now see here how the particles are tracked from one frame to the next. And now it's done here in this way that since you usually capture videos of quite a long time, you can now just assign that every 10th frame you want to be the features to be detected and be tracked, for instance, across 15 frames. And then you add up this information and get a dense velocity field for your area which you're observing. But if you're looking closely here now on the tracked particles, you can also see that there are still some outliers within due to ambiguities, for instance, which have to be filtered. And therefore, since we are now observing a river and we can assume some characteristics of the flow of the river, it's possible to filter out some of these faulty tracks. On the one hand, you can consider the flow characteristics, such as the main flow direction, and as well as the steadiness of the particle, because you're not assuming a jump to the left and right of the particle while it's flowing through the river. And furthermore, you can also, of course, look that the particle has to be traced across at least a minimum number of frames to be sure that indeed a particle has been tracked. And so here you can see now results of the unfiltered tracks versus the filtered tracks. And now the processing is nearly done within the images. And in the next step, you want to estimate from which location that image or the frame has been captured to afterwards scale the velocities, which are now still in pixels per second. And therefore, you need to know the camera pose as well as the water level. And the camera pose can, amongst others, be estimated using a spatial resection and by considering ground control points, which are now here highlighted with the red squares. And after you know the pose of your drone and the interior geometry of your camera, you can now project your image, your tracked particle, the position in the image through the projection center and intersect it with the water surface, if you do know the water level, and then actually calculate afterwards the velocity in meter per second, which is the result you can see now here. And of course, you have to consider the video frame rate to get the correct velocity. And again, as with the water depths, of course, you want to analyze the accuracy of your approach. And here you can see now there have been 3 cross sections which were measured again with the ADCP, because the ADCP does not just use the travel time of your sound wave to get the water depth or distance in general, but it also uses the Doppler effect of the sound waves, which are scattered back from the particles moving in the water. And it analyzes this frequency shift to at the end get the velocity of these particles floating in the water. And so this has been done here, and it has to be noted that, of course, it's not possible to get the surface velocity, only the velocity at the minimum depths as you are using the sound waves reflected from the particles. And for this ADCP, you have to have a measurement depth of at least 20 centimeters. So the velocities which are here shown are actually from depths of 20 centimeters. And now here you can see the results, which are now that the UAV velocities are compared to the ADCP cross sections. And on average, the deviation range between 0.03 to 0.05 meter per second, which is a good, which indicates a very good suitability to use a UAV to actually measure flow velocities. And as you also can see, in all 3 scenarios, the velocities are overestimated by the UAV because you're actually measuring the surface, which is in most scenarios flowing faster than areas underneath. And now the second part would be talking about not just using RGB imagery, but also using thermal imagery to get flow velocities, because you can have scenarios where there are no particles on the water surface, which you can track. And then the idea is to see if it's possible, especially also for large rivers, to rely on the temperature differences to use them as a signal and trace it with you trace it again. And here in this scenario, it was again at the Sayo River, and the UAV was hovering above the area over here. And then videos or frames were captured with a thermal camera, and it was the FLIR 8065, as you can see shown here. And the flying height was about 60 meters, and images were captured every half second. And the images were captured in a 14-bit RAW format. And the camera itself has a sensitivity of 0.05 degrees. So it means that you can differentiate temperature differences of 0.05 degrees. And now here you can see the unprocessed raw, unprocessed images of the thermal camera. And of course, again, you can see very strongly the movements of the UAV. And you also can see now in this image, it's an 8-bit image, and the gray values are stretched over a temperature range of 5 to 25 degrees, because the shores were a lot warmer than the water. And so in this image, you do not see anything yet or any temperature signatures in the water, as the water only has a temperature range of about 2 to 3 degrees. So in the first step, the shore areas were masked, and then again, the gray values were stretched to only the temperature range of the water. And now you already start to see a thermal signature in the water, which is floating upwards. And again, we were also accounting for the movements of the UAV by performing an image stabilization. It's the same as for the co-registration for the median image or the other RGB-based approaches. And now you can see the thermal signature, as well as some very dark spots, which are very cool ice cubes, which were thrown into the river to also indicate the flow. However, now the signature is still quite weak. So in a further step, here there was some adaptive histogram equalization performed to consider that the contrasts are here locally different. And then here you can see is the result of this equalization. However, this also causes that noise is going to be enhanced. And here specifically the fixed pattern noise, which is a consequence that the uncooled thermal sensor, each pixel on it reacts differently to the incoming radiance. And though this noise is what you can basically see here by this column and row pattern. So therefore, also we performed at the end some smoothing to try to filter it out a little bit more. And now this is the final result. And you can now here very well see the thermal signature in this video sequence. And the last step is then to perform the tracking again, but this time not using PTV, but using PIV, which means that you are performing the tracking in stationary image sectors, which means that templates are extracted at the same position in each frame. And then you're trying to track the pattern. And therefore, the result is also here displayed in a raster compared to here on the right side, where again, PTV has been applied to the RGB imagery. And PTV is not working here for the thermal images because there are no very distinct features on the water or in the thermal signature which you can use to trace. And you can see now here that the velocity patterns are similar. However, the thermal imagery are a little bit lower than the RGB imagery. And the comparison to the ATCP measurements, which you can see up here, which have been performed here with the cross-section, the deviations are about 0.15 meter per second for the UAV data. And now I've always been talking about how to use UAVs to measure the flow velocity at hovering positions, but the ultimate goal is going to have actually flow velocity fields of the entire river reach. So in the next step, this approach from stationary position has to transfer to the entire river reach. And so therefore, again, the UAV was used to fly along the river. And actually the same video, which has been captured to calculate the median image, is now again used, but this time for the tracking of particles on the water surface. And the approach is the following, that again, you're extracting the individual frames and you assign a head frame and then co-register the frames, the tailing frames to the head frame, and repeat this every nth number of frames, as you can see now here. And then again, you co-register the frames, and each of these head frames are used within the standard UAV photogrammetry orthomorphic flight. So to also get the pose from these head frames. As you can see now here in red, these are the positions from which the head frames have been captured. And so in this, you already have now the information about the pose. And afterwards, what you else need is, as mentioned, you have to know the water level to get the correct velocities. And therefore, you now use the extracted 3D contour, which I was already showing in the beginning, and you consider this information, and now consider only the 3D contour, which is visible by each of within the field of view by each of these head frames, and then you just average the height values to get the water level of the using the 3D contour. And furthermore, as mentioned, you have to mask the water area in each of the frames. So what you now also need is the points under the water, and you project these points back into each of the frames and say where these points are landing, that is the water area, and so you can mask the water, which you can see now here with this contour. So this is the area where you have the water, and the left and right is the shore. And the last step is then going to perform again the particle tracking velocities to get finally the velocity of the river. And here you can see the result for all three rivers. And you can see now that you actually get a quite dense velocity field of each of the river. And this is now a very valuable information also in the next step for hydrodynamic modeling, for instance. But you can also see here that depending on how many particles you actually have on the surface, that the density of trace particles is different. For instance, here at the left on the Freiberger Mulde, you have areas where you have nearly no particles which were traceable or only within the main flow. So these are still some things where you can improve the workflow by, for instance, using the thermal data. And now again, some accuracy assessments which were performed here for the Pulmanki River and the Sajo River, so in Hungary and in Finland. And again, here, ATCP measurements, the same ATCP measurements which were also used for the water depths are now used for the flow velocity. And you can see here now the average deviation between the Sajo and the Pulmanki River is about 0.02 and 0.05 meter per second. And you can also see here is also implemented the Freiberger Mulde, but here the reference were not ATCP measurements, but current meter measurements. I'm not going to focus here on the Mulde, but only on these two rivers. Because here you can now see also a scatter plot of the velocity of the UAV drawn versus the velocity of the ATCP. And you can see general, of course, that there is a trend visible, but you can also see that there is still quite some high scattering. But again, it has to be noted that this is not sure that it is due to the UAV data. It could also be partly due to the ATCP data, because the positioning of these ATCP points were only possible here with 30 to 40 centimeters. And in the rivers, you can have quite strong velocity shifts already within shortest different distances. So this might also be a reason for the deviation between both approaches. And now the last step for the hydrological application, at least, is now to actually try to see if you can use the flow velocity information as well as the bathymetric information and the water level to at the end get the discharge, which is a basic input parameter for hydrological modeling as well as hydrodynamic modeling. And the approach, what you're doing to get the discharge is basically you have your wetted cross-section through which the water is flowing, and you multiply it by the flow velocity to, at the end, get the discharge in cubic meter per second. And to get even a more accurate discharge estimate, you usually subdivide your river cross-section into smaller areas, and then you also measure the flow velocities not just at one depth, but at different depths, as you can see here by these black dots. And then you use those information to get a more precise discharge estimate. And you need to do these measurements now at different water levels, because as the water level changes, the velocities change and the discharge changes. And at the end, the goal is to derive a rating curve for later applications in modeling or whatsoever. And the rating curve basically relates the water level to the discharge. So you have to do these very time-consuming measurements at different water levels to derive later the discharge or the rating curve. And you further have to consider that as soon as the cross-section is changing because of sedimentation in the cross-section, you have to go again and measure the discharge again at different water levels, because then the whole rating curve is going to change. And now the idea and the advantage of the UAV is now that it's very flexible and that you actually can go doing very different scenarios out and measure the flow velocities, and also, if the water is clear enough, the bathymetry. And then what you do is you pick location which you already can decide which are very suitable, because you have enough points underwater as well as velocities covering the entire cross-section. And then you extract the points at these cross-section, as you can see now here at 1, 2, and 3 at the river in Hungary, the Zajo, and here at another 2 cross-section at the river in Finland. And then what you can do, you can average these points and calculate the cross-section area by knowing the water level at each of these measurements. And multiply it again with the velocity, with the surface velocity. However, since the UAV only measures from the surface and not at depth averaged velocity, and as I already mentioned, the velocity in below the water surface are slower. Here in this scenario, the velocity has been multiplied by a correction value of 0.85, which is stated in the literature, and then the discharge is correspondingly calculated. And now here you can see on the left side is the reference from the ATCP, and now the measurements of the cross-section discharges from the UAV data for the Pulmanki River and the Zajo River. And you can see that they are actually quite good in accordance, because the Pulmanki, the discharge is only underestimated by 10%, and at the Zajo even 8%. So this shows very promising results, which are worth to continue working on. And because in the future, this is also showing that it might be possible to capture entire river reaches and perform decision-based selections of cross-sections which are most suitable for the discharge observation, due to sufficient observation of the bathymetry and the velocity. And you also can now not just extract it at one cross-section, but several, and also do some statistical analysis to have a better idea about the robustness of the discharge you are estimating. And now I want to talk within the last 2 slides about what could be the next steps to go to from these measurements. At the moment, the whole measurements, they were all based on indirect referencing. So you had to distribute ground control points around the area of interest to actually get later some scaled information. But in the future, it will be very interesting, these RTK GNS developments on UAVs, to actually use those information and to not have to distribute ground control points. For instance, during flood scenarios, as you can see here on the left side, this has been a flood event at this Hungarian river. And during these scenarios, you don't want people to go out and put ground control points, as it is too dangerous. But you still would like to have information about the flow. So what you can now do is use the RTK GNS information to use direct referencing, and use that to, again, do the whole workflow as already introduced before, but now to get the scaled velocities without any ground control points. And this has been done now here for this flood event. And on the right is, again, just as a reference, or comparison, the low flow measurements where we use the ground control points. And here are now the results of the velocities, which already indicate very interesting findings. At the one hand, of course, you can see that the velocities, they are at least plausible, but it has to be noted here that due to this high risk situation, there is no reference measurements. So it's not possible here to assess actually the accuracy of the approach, but which can be done in the future in studies under more safe conditions and using direct referencing. But what you also can see, if you compare the flow pattern during the flood and during the low flow conditions, you can very well see that the main flow is changing its main path. So this is another very important information, especially for the hydrodynamic modeling, to see actually how the flow velocities are changing and especially changing at different water levels. And with this slide, I would like to finish my presentation. And thank you very much for your attention. And I'm looking forward to your questions.
Thank you, Anette, for your great presentation. It was a very interesting talk. Do you work in a very challenging scenario, which is use image to estimate some water parameters? And the water in general is very similar. The water is homogeneous, and maybe this make this challenging task, in my opinion.
Yes,
I believe that you also agree with me, and for this reason you are working on this thematic.
Yes.
And as you mentioned, you use the RGB thermal camera using both on terrestrial and also on UAV, and also assessed those results using some ground truth information. So I made some questions regarding the accuracy, but I was thinking, but in the end, you include the accuracy, and for me, it's okay. The results are very interesting, and also you assess the activity results. And
yes.
Congratulations for this.
Thank you.
So I would like to invite Professor Mauricio to make some questions. I don't know if he has some questions.
Okay, I have some. First, Annette, thank you for the presentation. It was very clear and the work is very interesting. And there's a lot of applications in Brazil, especially. It's have a great interest. As you show, you use the normalized cross correlation function to co-registrate the points in the water surface. Consider the point that Marcato told that some parts the images are too homogeneous. Can you give some details? Which elements were considered in the filter strategy to eliminate wrong matching points?
Yes. So as you say, indeed, the water surface is very homogeneous, but actually on the rivers, it's not as homogeneous as you would think, because as soon as you have a high resolution images, and that's the advantage of the UAV imagery, you do have these resolutions where you actually very well can see lots of particles floating on the river. Even from the distance, it does not look like that. But actually, yeah, as to your point with the normalized cross correlation, it's now, I showed you here some results with that, but of course we're also using least square matching, which actually performs even better because due to the particles, they are deforming on the water surface and they are rotating, and then the cross correlation is not performing as well anymore. And then so that's another thing to consider. And yes, but you still have ambiguity, so particles looking similar. And so one thing you could do is either using the an image permit, of course, to refine your and avoid these ambiguities. But also, as stated here, if you have very big jumps, for instance, between one frame and the next frame, you can use this kind of assumptions as you know that how the flow in general is going to behave in rivers, and you can use that for the filtering.
Okay, thank you.
We have a question, Professor Mauricio, from the audience.
Okay.
Nayara, could you read for us? It's related to the multi-sensor and fixed wings UAVs.
Yes. Can we add that if you want to film, you will have to deal with multi-rotors since you fix wings and it wouldn't be possible?
Yes, indeed. I don't think, I mean, I did not try it for fixed wings, but I'm very skeptical that this would work because you need a quite low flying velocity along the river reach. And the frame rate of the video has to be high enough. And for the fixed wing, I think it's not going. I don't know what the minimum speed is, but I don't think I think it would be not stable enough, or the danger would be too high to crash the fixed wing.
Nayara, do you have more questions?
I have. I would like to ask you, are there any restrictions on the use of frames to measure the speed of the river? In other words, can we use this method for any water flow or river feature?
So you mean the restriction regarding the velocity of the flow, or because I mean, of course, if it's going to be a very fast-flowing river, the frame rate has to be sufficiently or high enough. But as shown here for this Sayo River, at least, the frame rate was only 0.5 frames per second, and it still was working in this scenario. But of course, if you have more frames, then it gets more reliable, also your velocity measurements. And we tested it at least with 30 frames per second, also for up to 4 meters per second, and it's also working. But it gets more and more challenging, and you have to assign good approximation values within the next frame where to search for. And if it's only moving very slow, very short distance from one to the next frame, it's a lot easier than when there's going to be big jumps from one frame to the next to actually find again the corresponding particle.
Yes. Professor Mauricio, we have a question from Jefferson. Could you read it for us, please?
Okay, Jefferson told that very nice talk. Thank you again. And how do you believe UAV could help flooding monitoring?
Yes, so I think it can be very, very helpful. And already now here illustrated was for a flood scenario at the Sayo River, which was actually a flood, I think a 50-year flood event, which was measured there. And also, but for the future, what would be also interesting to further look into these RTK possibilities, and also regarding that it's now actually possible to have the UAV hovering very stable now with this new IMU and RTK technology, that you don't even have to necessarily co-register the frames anymore. So this would be another thing for the future, that you actually can hopefully do processing already in real time on the UAV and get the velocity values transferred to the people who are ever in charge of then the catastrophic management.
Okay.
We have many questions, Annette. It's very interesting. Yes, we have a question now regarding the ADCP velocity measurement. What are the ADCP velocity do you use to compare with UAV velocity? One transect or a mean transect like VMT?
Yes, here in this approach, we indeed we did not use the mean transect. And so this is another point why this deviation might be so long, but might be quite large at some parts, because of course, if you do this mean transect measurement, then you of course get a more reliable velocity values also by the ADCP measurements. So, and we used, as asked here, indeed the first cell below the water surface. So the first measurement that was possible under the water surface.
Professor Mauricio, do you have any other question? Please feel free. After that, we can answer the audience.
Okay, no, I have, but let's introduce the questions from the audience. From Mohamed Ramalia. How do you believe UAV could help dry and wet season monitoring in Indonesia? And can UAV monitoring the characterization and the quantification of migration patterns of the river?
Yes, I think that is a very good question. And also, one idea, of course, would be to use the UAV, not necessarily with the pilot who's going there and measuring, but having, because these devices are already also available, using a drone which is fixed at some area of interest, and then you do just autonomous flight and capture your data frequently, and then you could use that as further analysis in this regard. So I think it can be possible as soon, or hopefully, if these the laws are changed in that regard, that autonomous flights by the UAVs are possible for these kind of tasks.
Okay, very interesting.
Nayara, we have other question here from Rodrigo.
Yes. Rodrigo said, very impressive work. Could you tell us if you test your software in rivers with highest suspended sediment transport?
Yes. Yes, the highest suspended sediment transport. No, we did not. Indeed, now here these are
concentration.
Oh, I'm sorry. Yeah. Here is the scenario. Indeed, were rivers where we had a very clear water and could see the riverbed. But as you also could see during the flood event, which was the last slide, you can see, of course, here you are not able to see the riverbed because of the high sediment load. And in these scenarios, one idea would be, but this depends, of course, how strongly the river cross-section are changing during the flood event, to either use post or pre-flood measurements, again with the UV, since it's so flexible, and then, for instance, for the discharge estimation, update the river cross-section based on that information.
Very.
Can I do one question?
Sure.
Anette, in your work, the focus is in the use of RGB and thermal images collected from UAV platforms. In your opinion, and consider that this kind of applications, what is the trend in terms of incorporating other sensors in this kind of platform?
So you mean, for instance, looking at satellite data or airborne?
UAV platforms.
Yes. But what you mean? I'm sorry, I don't understand the question. What do you mean? How?
In terms of incorporating another sensors.
Putting other sensors,
yeah,
of course.
Instead of RGB and
another
camera.
Yes. For instance, also for the mapping of the rivers, of course, another very interesting or already well-tested approach would be using a LiDAR on the drone as well, to also get because here you can already very well see that if you fly along rivers which are strongly vegetated, then you also get to your limits with this set mapping. And usually many rivers have quite large vegetation cover along them. So combining it with LiDAR is then would be another important aspect to consider and to make it applicable even to other areas.
Okay, and in this case, there are some active systems like LiDAR in green band that are used to recover swallow underwater surface.
Yes.
Have you compared your results with this kind of results? Or
I did not compare it, but I know from other studies they actually use LiDAR data as training data, and then in combination with machine learning to correct the underwater points from the image data. So there's also a very interesting combination of these things. Yes.
Okay.
But the LiDAR data, of course, or the LiDAR itself is for many applications a lot more expensive compared to the images.
Yes. One interesting point of your work is that you use normal cameras in a UAV platform, but you work hardly on the method to recover the speed, the velocity, and the depth, and this is an interesting point. It's complete. If you problem the cost of a green LiDAR system is very expensive compared to to your work. But
Nayara, we have a question from Pedro. Could you read, please?
Yes. Pedro asked, did you conduct a sediment campaign to determine the particle diameter? How did you calculate the distance from the camera and the particle per interrogation window or the other PIV parameters?
Yes, for the first question, we did not do any sediment campaigns to compare the particle diameters. We really just rely on what's on the water surface. And so in some rivers, it might not be suitable anymore if you go too high and you're not able to see the particles. But for instance, at the Finland side, it was during autumn and you had a lot of leaves on the water. So it was there, it was very well suitable. And for the distance to the camera, for the particles, so that was I was explaining before that, for instance, with the ground control point and your typical UAV photochromatic workflow, you can get the pose of the camera, so the orientation and the position, and then you have to get the water level, for instance, by using the 3D reconstructed point cloud and look where the border is and get the 3D information of or get the water height. And then I just intersect the image measurements through the projection center with the water level, and then get the actual information on the position of this particle in the object space. And I do that from particle to particle, and therefore get then the velocities in meter per second.
We also have other question, Professor Mauricio.
Yes, the question, any work on remote sensing the chemistry of the river? Is it a possibility?
Yes, I'm not really able to answer that question because this is not the focus of my work, but if I'm correctly aware of, or if I'm remembering correctly, there are at least works now using multispectral cameras and trying to see how well they can use, at least I know, of course, you can use hyperspectral cameras that as they use in geological applications. And I think they're also now testing it to if it's possible to get some idea for the river, or at least I could imagine that this might be something also not just applied to identify minerals or things like that, but actually to see the chemistry of the river water. So yes, I think using UAVs with hyperspectral or multispectral sensors should be possible or could be possible in that regard. But I have not done anything in this area.
Okay.
Nayara, do you have any question?
I have one. If you intend to estimate flow velocity, what do you suggest to use, RGB or thermal sensor?
Yes, that's a good point. I mean, in the best scenario would be maybe a combination of both, because as shown in this application here at the Hungarian River, you had the particles floating at the surface at another area as where you had the temperature signatures. So by combining, you get actually the entire cross section. But in other scenarios, I think the thermal signature is going to be more complicated the smaller the river is going to be that you actually can see something. But I have not tested it, but yes, so it depends really. Of course, and the thermal is more expensive to use versus the RGB, so it really depends.
Mauricio?
Only in the first part of your presentation, where the depth of the water is determined, in this case, the images were co-registered considering only points outside the water surface, correct?
Yes.
And,
so, yeah, that can be another limit, of course, if you get depending on, of course, you can always go higher, but then the resolution decreases on how wide the river is going to be. And if you have like a braided river, maybe with very large river width, then this might be also more complicated. But then again, if it's a braided river, you also have river banks in between, which you might be able to use.
And in the estimation of depth, how many images, the minimum number of images that you consider that is good to have a good accuracy, enough accuracy?
I don't think there is going to be a number in that regard, because it depends also on how strongly on the one side the UAV is moving. If it's moving very fast, then you cannot use as many frames to co-register it to the first frame. And also how complex the water surface is actually behaving. If you have very strong waves or if you have only a few, this all depends on the different scenarios, what might be a sufficient number. Here in these scenarios, we used between 5 to 15 frames to get the median image.
Okay.
We have a question regarding the CNN model that you showed to us in that animation. Do you have to train a CNN model for each camera position, and how did you do training this model for water surface segmentation?
Yes, this in this work it's together with Makato, and what here it was chosen for just one camera position, but this is actually now ongoing work to see how well it's transferable to other camera positions. So regarding this first part of the question, and the model was trained by indeed segmenting manually segmenting the water areas. And then two different models was used. So the one was FCN and the other one was SegNet to, at the end, see how well they are able to classify the water area. So they were fully connected convolutional neural networks. And I'm sorry, fully convolutional neural networks were used.
So, Annette, one question is regarding when working with river, we can remove, we have to mask the vegetation. How did you conduct this? Is it a manually annotated procedure?
You mean for what? Here in this case, I did not remove the vegetation, but in other application, when you really just want to know the topography, then we used here it's a point or it's a filter based on the point cloud itself. It's called Canubo, and this has been applied here to get the vegetation and to filter it. But I did not show any results in this regard here in this presentation. But it's possible, but of course you lose a lot of information. And if you would use a LiDAR, it would be a lot more, you get a lot more detail also underneath the trees.
Okay. We have more questions here. Mauricio, could you read for us?
The question from Rodrigo Pereira. In a future perspective, it is on your plans estimate suspended or bed load transport rates using UAV method?
Not directly yet, but for instance, of course, you could try to use the color of the water and to see if you can and have them in situ measurements and try to get a correlation between those two and apply that. But then this would be also only be valid for one river, and you would. But I'm pretty sure probably work is going on in this regard already, tend to transfer to many more rivers and actually train then, depending on the color of your image, maybe to get an idea about the suspended sediment. But for the bed load, no, there is no work going on. The only work what might be, or the UAV bed data is going to be used is actually to get the discharge and the velocities and the pattern of the velocities and then combine it with a hydrodynamic or hydro-morphological model to get them some idea about the bed load transport.
Okay.
Very nice. I have one question, Annette, is related to the last part you showed, the discharge estimation. And the discharge depends on the flow velocity and of other parameters that you can estimate with UAV.
Yes.
I don't remember regarding the accuracy because we have errors during this process.
Yes.
Could you discuss with us
Yes.
something related to
of course,
discharge estimation?
Yes, and especially these discharge estimations, they get the easier, the more you have a really like a very simple cross section, and the more complex the cross section is going to be, it more going to have deviations. And if you start to have even then some data gaps that you don't have the velocities across the entire cross section, this will further increase your errors in the velocity. In the discharge estimation. And furthermore, the water level has to be known very precisely, because having it wrong a few centimeters already completely changes the discharge estimate, as the wetted cross-section can already change significantly. So these are all things which makes this approach still very sensitive. And I did not show it here for the Freiberger Mulde because we did not have any discharge measurement there, only from a gauge a little bit upstream. but there it did not work at all. So we were off twice as much, had a discharge twice as much as was measured as a gauge. So there is still a lot of work which you can to improve that. For instance, indeed, also subdividing the UAV data in different cross-section areas and then doing the velocity estimation and the discharge based on these subdivided cross-sections. This is something else. And as mentioned, if you have it now for an entire reach, to actually look at different cross-sections, and if it's always putting out this nearly same value, that might also give you already an idea about the reliability of your discharge.
Very nice answer. And we have people from different parts of the world. Unai from Azerbaijan and Indonesia.
India.
We have people India, Brazil. Very
nice.
Yes, the online we have this advantage to join people from several parts.
Yes, that is really great.
I believe that our time is over. I would like to acknowledge you again, Anette, for your very interesting presentation. This presentation will be online in the YouTube channel of ISPRS and also from our GRSS student chapter. And so the video will be online. And thank you, Professor Mauricio and also Nayara, for being here with us. Make this event more better. Thank you again, Anette. And
thank you very much.
And only one point, we have other talk today at 3 p.m. here in Brazil. A very interesting topic in other thematic. And all of you are invited to join us on the next talk. Okay? Thank you, Anette, Mauricio, and Nayara, and see you later. Bye-bye.
Thank you very much. Bye-bye.
Thank you. It was a big pleasure here.
Yes, it was very much fun. Thank you.
Thank you for the invitation, and thank you to Anette.
Thank you very
for
much.
Presentation. Okay.
Thank you. Okay.
See you. Bye-bye.
Bye-bye.
See you.